Today we are going to talk about different type of stochastic process. So far we discussed about stochastic process defined on discretized time, and this stochastic process includes finite number of states. Now we are going to talk about a stochastic process defined on continuous time, and this stochastic process includes finite number of states. So you can think about two different graphs, and left side is about the first example, stochastic process defined on discretized time having finite number of states. So a representative example is a discrete time Markov chain we discussed earlier. So now we are going to talk about different type. And the simplest version of the stochastic process defined on continuous time is a Poisson process, or we call this point process generally. So we are going to start with Poisson process. To understand Poisson process, we need to understand a specific random variable called an exponential distribution, exponential random variable. This is very important random variable, and I believe most of you already knew about this random variable. So actually this lecture is kind of a review for exponential random variable and its properties. Exponential random variable can be used for modeling like a lifetime of the verb or components, or sometimes we can model inter-arrival time for a queuing system as a exponential random variable. So let's think about this random variable. If large X represent this exponential random variable with parameter lambda, we call this late lambda. And if this random variable has cumulative distribution function large F. Cumulative distribution function means probability that this large X random variable X is less than or equal to small x. Okay. Sometimes we can write this by large F of small x, and if this function has such a form 1 minus e to the negative lambda times x, okay, then as long as this random variable has such a property, probability that random variable is less than or equal to small x is equal to 1 minus e to the negative lambda times x, then we call this large x exponential random variable with late lambda. Actually, this cumulative distribution function is own characteristic of random variable. So as long as we know a certain form of cumulative distribution function, then we can name the random variable, for example, exponential random variable, and we also know the parameter, in this case, lambda. In other words, we can define this random variable with probability density function rather than cumulative distribution function. When we consider the first order derivative of cumulative distribution function, then we usually use small f of x. Small f of x is lambda times e to the negative lambda x for all non-negative x. Otherwise, we give 0. Okay. Then we call this random variable exponential random variable. By the way, for exponential random variable with rate lambda, we can, so I believe you know the mean value of the exponential variable x. What it is? What is it? 1 over lambda, right? And the variance of the random variable x might be 1 over lambda square. Okay. And the most important characteristic of this random variable is called memoryless property. Memoryless property is about how to calculate how to handle conditional probability. So the simplest version is for positive constants s and t. For given positive constants s and t, sometimes we want to calculate such conditional probability. So probability that large x is greater than small s plus t, given that x is greater than small s. Okay. So for exponential random variable, this is always true. Probability that x is greater than t. Okay, we can ignore the conditional part with some manipulation. So we can interpret this with an example, like when we consider lifetime of the verb, if the lifetime of the verb follows the exponential distribution with rate lambda 1, that means mean 1 year, let's say year. And then if this verb have been working during last 6 months, okay, then given that this situation, what is the probability that the verb will work another 6 months, 6 more months? Then this probability is the same as new verb is working with 6 months. Then we can consider this conditional probability as a new another but same random variable with greater than probability that this x another but same random variable greater than t. Very important. So sometimes we need to calculate some probability regarding conditional probability. But the thing is, as long as we know this relationship, then we can easily find the result sometimes. And another version of memoryless property, this is very important. If large s is independent of large x, I mean this s is here. So given that large x is greater than large s, what is the probability that large x is greater than small t plus large s? Okay. So we replace this small s by large s. This large s is a random variable. And as long as this random variable s, large s, is independent of large x, then we can apply the same rule, I mean memoryless property. So this probability is the same as large x is greater than t. But the thing is, unless this large s is independent of large x, then we cannot guarantee this result. So for example, large x is exponential random variable, and if we consider large s is, let's say, large x over 2. Let's consider this simple example. Then we try to calculate this probability. Right. Okay. And then, based on this situation, okay, what do we know? This one is actually the same as probability that large X is greater than large X over 2 plus T, and large X is greater than large X over 2. Probability that large X is greater than large X over 2. Okay. And then we can see that this T is the positive value. So this event can be included by the right event on the right part. So we can rewrite this. So, and this part can be ignored because this is always true. X is positive values, and X is always greater than X over 2. So this probability is always 1. So this whole probability can be rewritten by X. And this is not the same as probability that large X is greater than T, right? So based on the example, we can see that large S is not independent of large X. In this case, large S equals large X over 2. In this case, a memory's property does not hold. And we have two more important properties regarding exponential random variables. Actually, these properties are very, very important. Sometimes to develop some result or derive some result, we can naturally use this without any explanation. But one more thing is, to derive this result, we need to consider many techniques, and these techniques also can be used for deriving some other results. So let's figure out what it is and how to prove it. The first one is, here we are considering two independent exponential random variables, x1 and x2, and they follow exponential distribution, but with different parameters. x1 follows exponential distribution with rate lambda 1, and x2 follows exponential random variable with rate lambda 2. And the first property is about new random variable x, which is minimum of large x1 and x2. Then what is the distribution of large x, and what is the parameter of the distribution? Actually, the result is large x is another exponential random variable, and the rate is lambda 1 plus lambda 2. And I would like to explain why this one is true. Okay, here, suppose that large x1 follows exponential distribution with rate lambda 1, and large 2 follows exponential distribution with rate lambda 2, and x1 and x2 are independent. Okay, we have such a condition. Okay, then first you would like to figure out distribution of large X equals minimum of large X1 and X2. Okay. As I said before, a cumulative distribution function represents on random variable. Okay, cumulative distribution function is like a fingerprint of the person. Okay, so as long as we figure out cumulative distribution function or probability density function, then we can name the random variable and we can figure out the parameter. As long as we have the form that we are familiar with. Okay, so that means we can figure out some probability regarding large X. Let's say in this case, probability that large X is smaller than t, smaller than or equal to t. Actually, this one can be cumulative distribution function of large X. Okay. This one is actually 1 minus probability that large X is greater than t. Okay. Based on the definition of large X, we can rewrite this by minimum of X1 and X2 is greater than t. Okay. And the thing is, here is one technique to develop equations. So this event can be considered as intersection of two events. As long as two different events, let's say, as long as large X1 is greater than t, at the same time large X2 is greater than t, then these two events occurring at the same time represent this event occurs. That this event occurs. So they are equivalent. Okay. So we can rewrite this event by X1 is greater than t and X2 is greater than t. And we know that X1 and X2, they are independent. So this probably can be rewrite. Probability that X1 is greater than t times probability that X2 greater than t. And because X1 and X2 are independent. Okay. Now we can apply the characteristic of X1 and X2. X1 follows exponential distribution with rate lambda 1. X2 follows exponential distribution with rate lambda 2. So this one is the same as 1 minus e to the, actually 1 minus e to the negative lambda 1 t, right? And this one 1 minus e to the negative lambda 2 t, right? So as a result, because x1 follows exponential lambda 1 and x2 follows exponential lambda 2. Okay. And then we can say that this part is the same as 1 minus e to the negative lambda 1 t times e to the negative lambda 2 t. So this is the same as e to the negative lambda 1 plus lambda 2 times t. Okay. Here is the CDF of large x, which is the same as minimum of x1 and x2. So based on the result, this result, what we know is this random variable follows exponential distribution with rate. This part represents rate. Okay. this part under this yellow square, rate of random variable, exponential random variable. So in this case, rate is lambda 1 plus lambda 2. So every time you try to develop this equation and to derive step by step, you need to understand why this happened. You need to clarify why this happened first, and then you can go further and further, and then based on the final result, you can connect the result with what we want to prove. Okay. Actually, first one is quite simple, not that difficult, but the second one is quite difficult. So let's consider the second part. So we would like to consider the probability. We are going to consider the same condition. X1 follows exponential random variable with rate lambda 1, and X2 follows exponential random variable with lambda 2. X1 and X2 are independent. Now we would like to calculate the probability X1 is less than X2. Okay. To calculate this, we need to understand important concept here. Actually, to calculate this, we can apply law of total probability first, okay? Because we need to consider two different random variables inside the probability. So we can condition on one of the random variables. So from 0 to infinite, okay, let's condition on x1. The probability that large x1 is greater than large x2, given that large x1 is x. And then we need to multiply this by conditional PDF for x1. X, given that just PDF of x1 dx. Okay, so based on law of total probability, this left-hand side is the same as right-hand side. Okay, left-hand side, what we want to calculate is the same as integral probability that is conditional probability and times PDF of large x1. Then we can get the result. The thing is, this part, large x1 greater than large x2, given that large x1 is x1. Actually, in this case, this one is actually the same as probability that x2 is greater than small x, given that large x1 is equals x, right? And then we know that this large x1 is independent of large x2. So probability that x1, so let's say this event is A, this event is B, then this one can be written by A and B occur at the same time, probability that over probability of B. And then the thing is, this event, they are independent. Probability A times probability B, probability B cancel out. So actually this one is the same as probability of A. So what we know is this part can be rewritten by 0 to infinite probability that large x2 is greater than small x times actually PDF of x1 is lambda 1 e to the negative lambda 1 x dx. Okay. Then what is this probability? Actually 1 minus probability that large x2 is less than or equal to small x, and this one is CDF of large x2. So this one 1 minus e to the negative lambda 2 x, right? This part. So whole part can be 0 to infinite 1 minus e to the negative lambda 2 e to the negative lambda 2 x times lambda 1 e to the negative lambda 1 x dx. Okay. And then when we consider integral parts, then this one is negative lambda 1 over lambda 1 plus lambda 2 from and then e to the negative lambda 1 plus lambda 2 x from x is 0 to infinite. So if x goes to 0, then whole part can be 0. X goes to infinite, then whole part goes to 0. If x goes to 0, then whole part goes to lambda 1 over lambda 1 plus lambda 2. Actually, this one is 0 minus lambda 1 over lambda 1 plus lambda 2. So you can get the result here. Okay. So you need to memorize the result for two key properties. First one, if we consider minimum of large x1 and x2, this one is another exponential random variable with weight lambda 1 and lambda 1 plus lambda 2. If we consider probability that large x1 is less than large x2, then this probability can be calculated by lambda 1 and lambda 2. In this case, lambda 1 over lambda 1 plus lambda 2. If we consider probability that x2 is less than x1, then lambda 2 over lambda 1 plus lambda 2. You can derive the result with the same way. Okay. So you can work on examples. These examples are very important, and actually, second example is very difficult to understand. Actually, so you need to work on it by yourself. Maybe the second one is if you try to solve with only with your intuition, then I believe you made a mistake to calculate the result. But someone can calculate it. But most of you, I believe, if this one is the first time to calculate such probability, then I believe you will make a mistake when you only depends on your intuition to solve the problem. So please be careful. So next time we are going to talk about example 1 and 2 in the class, and then I'm going to talk about Poisson process after the example. So is there any question? We usually come up with a homogeneous Poisson process. So homogeneous means this event occur with the same probability at any point of time. Okay. So when we consider Poisson process, or as I said before, this one is a special case of point process. This process represent number. Okay. So usually we use large N represent number, and with parenthesis. Okay, inside parenthesis we can put some measure. Usually you consider time measure. Okay, so when you put amount of time in the parenthesis, okay, then this O N and parenthesis means number of event occurs. Number of event occurs during this amount of time. Okay, we call this generally point process. Okay, process means process represents such random variable. Okay, actually this random variable is function of measure. Okay, and usually we consider time measure. Okay. Okay. For example, if students arrive to the classroom randomly, okay, randomly, so arrival from anyone cannot affect on arrival of another student. Okay, this event occur independently. Okay, when we consider this, and we can count today from 10:20 to 11. Okay, we can count, or 10:20 to 10:30. We can count. Number can be different. Every day, different. Every class, different. Right? But as long as this event occurs with the same probability for everyone at any point of time, okay, then we can model this with Poisson process. So we can put the time measure 10:20 to 10:30, 10:20 to 10:25, 10:20 to 11, and so on. And then this, after put the time measure, okay, range of time, then we can come up with a random variable. Depends on this time measure. Okay. So N of t, large N of t represent number of events that occurs from time 0 to t. And we have a basic assumption: all the events occurs with the same probability, and these events are independent. Okay. So N of t represent number of event that occurs from 0 to t. And we have three rules. As long as this large N is satisfied with these three rules, then we call this Poisson process. Okay. If I have time, then I'm going to explain why this. Earlier I defined this process with some probability and independence, right, of the events. Okay, based on the structure. Okay. Based on the structure, this random variable large N is satisfied with this three condition. Okay, but this connection, to explain this connection, I need to add more and more discussions, but we don't have enough time. So let's define this process with these three conditions first.
This is a continuous variable, right? Because
large N?
Yes.
large n is discretized value, 0 to infinite, all the non-negative integers. Interval of time, you need to consider, you can consider any amount of time. This one continuous. So it is inside the parenthesis, you can put the continuous measure. But we can, after, when you consider all the measure n of parenthesis, this value represents discrete random variable. Okay? This amount of time, how many times event occurs? Okay? And first consider, let's start with the last one, n of 0. When you put 0 inside the parenthesis, so that means we need to count number of events from 0 to 0, right? Based on the definition, 0 to 0. This n of t represents number of events occurs from 0 to t. So when you put 0, we define this 0 always. Okay, first condition. Okay. Second, when we consider positive t, positive value t, n of t, okay, that means number of events occurring from 0 to t, right? Positive t, for positive t, t is greater than 0, and real number, okay? This one is actually random variable, okay, random variable, and this one follows Poisson, random variable with rate lambda times t. Okay. Okay. But sometimes we would like to consider not 0 to t, but s to t. Okay. If time we consider time horizon 0 to infinite. Okay, if we consider number of events occurring from 0 to t, then that might be n of t under some assumption, right? But if we consider number of events from s to t, s is less than t, okay, then that might be the same as n of t minus n of s, right? Number of events occurring from 0 to t minus number of events occurring from 0 to s. Then that means number of events occurring from s to t, right? Then if we consider this random variable, this one follows Poisson lambda times t minus s. So this one, this part represent amount of time, just amount of time we consider. This one is actually the same as n of t minus s, right? Actually it's the same. Because, as I said before, this one is actually based on assumption events occurring with the same probability, and they are independent. So this one is true. Okay. So later I'm going to explain the connection between the concept and this definition if we have time. But let's start with the definition first. Okay. So for s and t, s is less than t. For n of t minus n of s, this one follows Poisson from the t minus s. Okay. And sometimes, generally, we can put time measure with from and to. Okay. So This one is simplified version of how to represent Poisson process. Okay. If we consider number of events occurring from general S and T, S is less than T. Actually, we put this way, range from S to T. S is included in the range, and S is not included in the range, and T is included in the range. Okay, this one, when you put the amount of time, S to T, and always we consider positive values S and T. Okay, then this one is actually the same as N of T minus N of S. Okay, this is generalized version how to represent point process or Poisson process. So at the beginning of the slides, I explained that inside the parentheses we can put the time measure, right? But simplified version is just number, time. Then this one represents number of events occurring from 0 to T. But if we put a certain amount of time from S to T, then this one represents large N of T minus large N of S. Oh, okay. Okay, this one, yes, typo. Okay, I'm going to change. Okay, first condition. Okay, I need to change this S to. Thank you. Next one. And third one is very important concept. Okay, we call this independent increment. So independent increment can be mentioned with other type of stochastic process and very important structure. And actually, when we consider discrete time Markov chain, we also consider such property, independent increment. So let's consider different time ranges. So U to W and S to T. And there is no common area from this to this and this to this. Okay? Okay. Then we can construct two different random variables with these ranges, with this range and this range. So large N of U to W and large N of S to T. Actually, this one represents a Poisson random variable with rate lambda times T minus S. This one represents another Poisson random variable with rate lambda times W minus U. Okay? Poisson S to lambda times T minus S. Okay? Follows Poisson lambda times W minus U. And the thing is, as long as inside the parentheses, okay, inside the parentheses, if for the time ranges there is no common area, no common part between this and this, then they are independent. If we consider, as I said before, inside the parentheses, we can put the time ranges or time measure, right? And then, if we consider different time ranges, no common area, between two time ranges. Okay? And then we can consider corresponding large n. Right? Then these large n's, they are random variables, Poisson random variables, and they are independent. So later we can use it in the example to calculate probability. Okay? To calculate probability, sometimes it is very useful to use such conditions. So in this case, 3, 4, U less than W less than S less than T. They are point of times. Okay. Then N of U to W. Actually, this one is the same as N of W minus N of U. Okay. This one is independent of N of from S to T. This one is actually the same as N of T minus N of S. They are independent. Okay. So as long as large N is satisfied with these conditions, 3 conditions, then we call this Poisson process. But physically, in practice, we can understand this with some conditions like all the events occurring with the same probability, and they are independent. Okay? Then this number of events occurring from 0 to t is satisfied with these 3 conditions, and we call this Poisson process. Actually, homogeneous Poisson process, because this lambda is a constant. Okay? In this case, lambda is a constant. Later, we are going to talk about non-homogeneous Poisson process. In that case, lambda can changes as t changes. Okay? Even though lambda changes, we can analyze the system. But we are going to start with the simplified version of Poisson process first.